Okay, so here we're looking at conservation of energy, which is the main, the most important part on this energy topic. So, with conservation energy, it essentially says that all the energy provided at the start of the universe is all the energy we have right now. So we cannot create or destroy energy. Okay, so we cannot create or destroy it. What can we do? We can only transform it, or in other words, we could convert or transfer to other forms. So you need to actually find the proper definition. From in your dictionary. Okay, there's a statement. It's a universal statement, so you could find it anywhere. It's very popular. Some examples of conservation of energy: a kinetic torch. Okay, so that's a torch that you wind up. Okay, so you essentially has some sort of body. Inside there's a motor and there's a handle attached to that motor. Okay, as you wind the handle around, you've got some sort of kinetic energy, okay, and then it's going to get converted to some sort of electrical energy, which goes to a lamp, and that gets released as light energy. A car slowing down, well, as the car is traveling along, okay, so as that car is traveling along, it will have kinetic energy, just like in that light one at the start there. So it's traveling along. For the thing to slow down to rest, okay, so we're actually going to stop the thing, the kinetic energy must be 0. So where does it all go? Well, it must all go to heat and light in the brakes. Okay, and if you look at that one there, you can actually see, especially in like race cars, and if they're racing at night, so the Le Mans, you can actually see the brakes glowing red hot at night. Heat and light. The other option is if you own a Prius, it could actually be used to charge up a battery. Okay, so they actually use a similar system to that kinetic torch. So we had a question earlier about the 1200 kg car traveling at 40 meters per second. If it's doubled its speed, it's quadrupled its energy. We worked that out. What part of the equation is significant? Well, if you look at the kinetic energy formula, it's half mv squared. What's significant is that squared part. You're going to find a lot of the multiple choice questions that we look at will be in reference to that. Okay, so v squared, very important. If you double your velocity, you get 4 times the kinetic energy, not just double. That's why a crash at 100 kilometers an hour is far worse than a crash at 50 kilometers an hour. How much kinetic energy will the car possess? Sorry, I missed once it stops. Okay, well, 0. We've already just talked about that. 0 joules of kinetic energy. So where did all the energy go? Well, because of conservation, okay, that's an O and that's an N. Because of conservation of energy, then it needs to be, kept. You can't actually destroy that energy. I can't destroy all your kinetic energy to 0. It must go somewhere else. So I must go to heat and light. Okay. If work equals force times stopping distance, okay, force times distance, and the force was constant whenever the car stops. In other words, we have a certain amount of kinetic energy. Let's say it was 1,000 joules, and we want to make it to 0. We're going to do 1,000 joules of work. We're going to transform 1,000 joules of energy. So comment on the distance required to stop the car from 28 meters per second to rest versus 14 meters per second to rest. It's a good idea to actually work it out. Do work equals force times distance. What we're trying to calculate here is force, so it's just work divided by distance. Actually, no, sorry, trying to calculate distance. Let's get this right. So there's work divided by force. Okay. Now, if we actually work this thing out with a constant force, you could come up with any value to test your logic. Okay, you could put in 100 or 200. But if this bottom line is the same, if that bottom line is the same, and we're only going to change the top line, well, when you're going at 28 meters per second, this value at the top line is going to be 4 times as large. Okay, so that means the value on this side, because of the equals, the D, must also be 4 times as large. So it takes 4 times the stopping distance for your car. So there's your little car. If you stop there at 14, it's going to be 4 times as far if you are going at twice the speed. Here's some examples. You can cut these out and put them into your notes, okay, just as they are. So at the top there, the guy at the top has a potential energy, so that's essentially gravitational potential energy, and it's equal to 10 joules, no kinetic energy. As he starts falling down towards the water, okay, he's losing potential energy, but he is gaining kinetic energy. But at all times, these things add up to 10, okay? Once he reaches the bottom, he's just before he hits the ground, he has maximum kinetic energy. But then once he's hit the ground, this actually says kinetic energy is 0 joules, potential energy is 0 joules, but heat is 10 joules. Or you could even have some sound, okay? Here we've got a roller coaster going down a hill. Okay, a roller coaster doesn't have an engine. It's all its energy is provided from the first hill at the very start. So here we've lifted the roller coaster right to the very top. That is the amount of energy it has in total. Okay, so that's all the energy it gets. It requires a machine to get it there, and then after that it's just released and off it goes, and it can go for as long as it likes, as long as it doesn't go higher, or that the friction doesn't remove all the energy. So here we've got a roller coaster. So there's 2 steps to answering this. We need to find the total energy. Okay. Well, at the start it's got kinetic because of the speed, and it's also got gravitational because of that. So EK is equal to half mv squared. So you just put in the values for that. 500 times 5 squared. Okay. And it's also got some potential, so that's just mgh. So that would be 500 times 9.81 times 50. Okay. And then your total will be equal to EK plus EP. Now, when it gets to the bottom, it's at 0 meters. Okay, so it's got all of its potential energy converted to kinetic energy. Okay, so the total afterwards is going to be total after is all kinetic energy. Okay, so if we get this value, put it here. Okay, we work out the total before, which is going to be EK plus EP, and afterwards it's all gone to kinetic energy. So then you just find your total value and make it equal to half times 500 times v squared, and solve for v to find your final velocity. This one here, find the values. Okay, so at the very start there, we're going to have, let's have a velocity of 0. It starts from rest, actually. So velocity of 0. So what is its kinetic energy? Well, 0 as well. Okay. To work out everything else, I'm going to do this in a simple way by using gravity being equal to 10. Just makes my life easier. In your notes, you probably should look at using 9.81. Okay, but Okay, so we have 2,000 joules of potential energy, so we must also have 2,000 joules in total. So number 2, well, we're ignoring friction. Unfortunately for your questions you might get in your exam and so on, will include friction a lot of the time, so make life a bit harder. I can fill out my total energy already, 2,000, 2,000, 2,000. Okay, but what's going to change now is my relationship between potential and kinetic. If I go to point 2, I can work out, because of that height, I can work out how much potential energy it requires, or is gained at that height. So let's have a look. It's gained 1,500 joules. Okay, so that means the leftover must be kinetic in this case. So then we solve for half mv squared. So let's have a look at that equation. Okay, so if I want to solve for V, we've got 2ek divided by m is equal to, and square root of that is equal to V. Okay, so let's have a look. And we're going about 4.5 meters per second. Okay. Next one, number 3, you could work that out, but essentially potential energy is 0, and then work out the next 2 from there. Number 4, okay, we know the speed now is equal to 6, so V equals 6 meters per second. Okay, so we can work out the kinetic energy from that. It's pretty straightforward. So you can work out the kinetic energy first, and then you take off the kinetic energy off the total energy to find the potential energy, and then you go back down and you find that height from mgh. Okay, so that should be pretty straightforward for you. If we have a look here, we have a ball doing projectile motion. Okay, at the start here, it's got its max V. Okay, so that means it has max kinetic energy. Okay, at the top here, it's got its smallest velocity. It's not 0 because you have a horizontal component that is constant. Okay, because remember, it's constant horizontally. So at all times, the kinetic energy, in sense of going the horizontal way, will always be the same. So at the top there, there's no vertical velocity, so the kinetic energy is at its minimum. But remember, it's not 0, unless the ball goes straight up and then straight down. Maximum potential energy, well, it's the highest point, so it must be the maximum potential energy. Here you've got a truck doing its transformation, and you can see here that just before it hits the ground, okay, it will have some sort of, just about here, it will have its max kinetic energy. But then once it's stopped on the ground, that energy still has to go somewhere, so it actually increases the temperature of it. Sorry about the American values there. Efficiency essentially is saying, if you have the expression, how useful is this device? Is it worthwhile? In other words, how much does it make use of its incoming energy? Okay, so using any of useful energy, total energy, and wasted energy to complete the equation. Okay, I'm going to write this a different way, maybe. So let's write output over input times 100. Okay, so essentially, how much did you get out? What could that be referred to? Maybe useful energy, compared to input, which is your total provided energy. Okay, so if you put something like 500 joules into something, okay, but you only get 100 joules of useful stuff, then this thing is 20% efficient. In other words, 1 over 5, okay, times 100. So a crane does 80,000 joules of work lifting a 200 kg mass 20 meters into the air. Calculate the efficiency of the crane. Okay, so 80,000 joules of work, that is your input, or total in. Okay? What did it get out? Well, we got a mass going this high. Okay? So that is what you got out of it. So let's have a look at what energy was actually required to get a 200 kg mass 20 meters in the air. Okay, oh, where's that from? MGH. Okay, so we worked it out. 200 times 20 times 9.81 makes 39,240 joules. Okay, so that is actually what was required. So you can see it's almost about 50% efficient. Okay, so what is the efficiency? So the output, 39,240 divided by 80,000 times 100. So 49% efficient. Okay, the kilowatt hour is quite interesting. Bit of a clue here. Kilowatt, okay, which is power times a time. Oh, well, I got power T. Anyway, so power times time. Now we're going to look at something about that in a second. Okay, so power. See dictionary for definition. Essentially, it is how fast you're doing work. So you can define it by the word equation: power divided by power equals work divided by time. Okay, do that in words, you'll be fine. Unit, well, it's the watt. Okay, derived unit, make sure you can do that. Now, since work equals Fs, we're going to substitute the expression Fs into the formula for energy. So we've got the formula for energy: work equals force times distance. So, Fs. Okay, substitute the expression Fs into the formula for energy. Okay, so P equals, where's work in this formula? It's at the top there. So it's Fs divided by time. Now, hope you notice here is that that part there looks familiar. Okay, looks like velocity. So if we then simplify it, we get a new equation, which is power equals force times velocity. This equation is quite useful. Essentially, if you're applying a force to something and it's going at a certain velocity, the velocity tells you the rate at which you're applying that force over a certain distance, and so you must be using some power. So this is important in a case where a car might be going at 100 meters per second. Oh man, it's a bit fast, probably 20 meters per second, for a constant velocity, but it requires a force to overcome friction. And let's say that frictional force was 20 newtons, so which is 20 times 20, and that gives you your power to overcome friction, because all the energies there are going to overcome friction. Remember, you don't need energy to go to constant velocity. This is pretty straightforward. Okay, power equals Fv. I won't do that one for you. It's pretty straightforward, and that is it. Okay, make sure you answer the question in the survey. Fields of